Okay, day 2 of 4.3. Let's look at this problem again. So this one we looked at yesterday, right? So you should be pretty good at graphing the derivative and the second derivative now. Right? We said yesterday to find the derivative, we just look at the critical points and we graph those, and then we say, is it increasing or decreasing? And then we kind of draw this graph, right? So that is f prime. If you drew this yesterday, you don't have to draw this again. And then we said from the first derivative, we can take another derivative and figure out the second derivative. Okay, second derivative shows that c is going to be a point where it's 0, and the graph decrease first and then increase. So that means the slope is negative and then positive. So like that. This is second derivative. All right, so yesterday we learned first derivative. What does that do to the graph? We said first derivative, last week we learned about critical points. We said first derivative, what makes it 0 and undefined, those are critical points. And then yesterday we learned, draw a sign chart out of the first derivative, figure out where it's increasing, decreasing, and then from increasing, decreasing, try to figure out the maximum, minimum, okay? Today, we are going to learn what second derivative does to the graph. Okay, so if you look at the second derivative, let's look at the second derivative. Second derivative, which is the green, has a very special point on c, right? c is 0, so that means something is special about this point. Let's look at this point and all the way back to the red, which is the first graph, f of x. So at this point, something happened. Okay, something happened. What happened? If you look at the graph itself, this is the shape it started with, and then it changed to this shape, right? It was kind of curving down, like a downwards parabola, and then it changed to an upwards parabola, right? Okay, so this is what we need to discover in second derivative. So let's kind of do this. So there's a name for this. This is called the concavity. Concavity tells you the shape of the graph, kind of like if it's curving down or is it curving up. And when we say concave up means it looks like this. It's like an upwards parabola. Concave up means like an upwards parabola. And concave down means that you have a downwards parabola looking thing. Okay, this is the concavity. And all of this has to do with second derivative. All right, so let's look at the definition of concave up. So f is concave up at A if, this is a little tricky. If the graph of f is above the tangent line to f at A for all x in a neighborhood containing A, but not equal to A. The graph of f is above the tangent line to f at A for all x in a neighborhood containing A, but not equal to A. Okay, so I'll show you what this is actually talking about. So it's concavity at a single point, and then we're going to talk about concavity at an interval. So right now, it's just at this point, is it concave up or down? So to figure out if it's concave up or down, we need to look at some kind of tangent line to this. In the parentheses? Yeah. But not equal to A, sorry. All right, so let's look at our graph. Okay, so if we look at this graph, so concave up is at around C to E, right? That's going to be concave up. So the definition says if you are concaving up at, let's say, D, then it is the graph, so the red part is above a tangent line at D. So basically, if you draw a tangent line at D, the graph is above that line. That's what it's saying.
Above which line?
Above the tangent line at D. So tangent line meaning the tangent line at D, the graph will be above. Okay, so concave down is the same thing, except they said if you're concaving down, so between A and C, you're concave down, right? You're kind of pointing downwards. So let's say you're concave down at B. Okay, concave down at B. They said that the definition says if you're concaving down at B, then if you draw a tangent line at B, so draw a tangent line at B, your graph will be below that tangent line. Can you guys see that? Yeah, so that's the definition of concavity at one point. Okay, so let's write that in. So basically it's the same thing. So concave down if the graph, so everything is the same except you're going to say it's below the tangent line. The graph of F is below the tangent line to F at A. Let me put this quote. For all X in a neighborhood containing A, but not equal to A. Well, concavity is not defined at a. Yeah, let me go check the book again. I think. Yeah, let me check the book again. Concave up, concave down at a point.
So, I mean, local extrema is also concave.
Great question. We're going to check that. Okay, next, concavity test. So, how do you know if something is going to be concave up or down? Did you guys finish copying? Not yet? Almost? So how do you know if something is going to look concave up or down, besides just kind of looking at it? Sometimes it's not as easy looking at it. It's kind of tricky. So let's look at this graph. We can see that at B, it's going to concave down, right? If you look at the second derivative, which is the green, so B is concaving down. If you look at the second derivative, is it positive or negative at B? Negative, right? At B, the value of the second derivative is negative. Okay, at D, which is concaving up, the second derivative, is it positive or negative?
It's positive.
Positive. So second derivative, we can use second derivative to tell us whether it's going to concave up or down by looking at the sign. So if the second derivative is greater than 0, that means it's positive for all x in I meaning an interval, then the graph of f is concave up on I. So second derivative, if it's positive, then your graph is going to concave up in the original graph. Okay, same thing for second derivative less than 0. If the second derivative is negative for all the x in interval I, then the graph of f is concave down on I. Okay, so if second derivative is negative, then in the original graph, you'll see that it's like a downwards parabola. Okay, just to make things a little bit trickier, concave up and down, we are not going to include endpoints. Okay, so increasing, decreasing, we include the endpoints. Concave up and down, when we talk about interval, we don't include the endpoints. Okay, let's look at our graph. Okay, on this graph, we said that the C is a very special point, right? The C makes the first derivative 0. So let's talk about these special points from yesterday. What do we call B and D in the original graph? Maximum, minimum. And then there's another name for those points.
Critical numbers.
Yeah, critical number or critical point. And we said critical point makes the first derivative what? 0 or undefined. All right, so now let's talk about C. C makes the first derivative 0 or the second derivative 0. I'm sorry, makes the second derivative 0. So this point makes the second derivative 0. And this is called the inflection point. Only if the concavity changes. So inflection point only if it changes from a up to a down or a down to a up. That would be called an inflection point.
The original function should be at least 30.
That's a good point. Yes. I think, let me see. Okay. Okay, we're going to say that we're going to put first derivative here. We're going to put second derivative here. Sorry. And then we're going to say that first derivative here is positive and it's negative here. And then second derivative is positive and negative here. Okay, let's look at first derivative because we did that yesterday. If first derivative is positive, what does that tell us about the graph? Increasing, right? So that tells us we're increasing. If the first derivative is negative, what does that tell us about the graph? Somebody. If the first derivative is negative, what does that tell us about the graph? Decreasing. All right, let's look at second derivative. We just learned it. So it might not be practiced yet, but we'll do it together. If the second derivative is minus, is it concave up or concave down? Down. If the second derivative is positive, is it concave up or concave down? Up. Okay, so in these 4 boxes, we're going to draw how the graph would look like. So, for example, for this first box, we're going to draw a graph that's increasing but concave up. Okay, so go ahead and draw what you think it should look like, how you think it should look like. It's going to increase, but it's also going to concave up. Just a reminder, concave up means that you're going to go up like that. It's like a smiley face, concave up. So how do you draw a graph that's increasing but only concave up? Okay, talk to your partner if you get stuck. You're like, how does this look?
I'm still writing this down.
Oh, okay, go ahead. Yeah, so talk to your partner if you get stuck. How do you concave up but only increasing? Okay, so basically, how do you draw this concave up but only increasing? Okay, talk to your partner. Concave up looks like a smiley face, right? A parabola. But you can see that both sides, this side is going to decrease. This side is going to increase, right? So how do you draw the graph so that it's only increasing? Only the right-hand side, right? Yeah, so like that, okay? Go ahead and try to guess the other 3. All right, so this is concave up but decreasing, concave down but increasing, concave down but decreasing. All right, now let's talk about that special point C on our original graph. Okay, so let's go ahead and write down inflection point. So inflection point, the definition of inflection point. So a point on the graph F is an inflection point if, first, F is continuous at that point. So obviously, we can't have an inflection point if the first original graph is undefined. You won't even have a derivative, right? Second derivative has to be 0 or does not exist. The third thing, and kind of the most important thing, is that it has to change concavity. So F changes, bless you, from concave up to down, or concave down to up. So the original graph changes from up to down or down to up. So there's like a very distinct direction, or not direction, but like a concavity change. Or sometimes it's really hard to see if it's concave up or down. So we check at the actual second derivative. Second derivative changes from positive to negative or negative to positive. So there's a very distinct sign change. Okay, so one, you check the original graph and say, oh yeah, it changes the concavity direction. Or you say second derivative, it changes from positive to negative. All right, we are ready to solve some questions. Let f of x equal this thing. So go ahead and copy down this equation first. F of x is equal to x plus 1 squared times x minus 2. Okay, the first question says, find the interval that f is increasing or decreasing, and find the local extreme of f. So that's last night's homework. So go ahead and figure out where is it increasing, decreasing, and where are your local extrema. All right, so let's kind of look at this together. So our critical points are -1 and 1. And our sign chart goes positive, negative, positive. Yes? Okay, increasing negative infinity to -1, 1 to infinity, decreasing, -1 to 1. To figure out whether something is going to be an extremist, you kind of draw the arrow on your sign chart. So increasing, decreasing, increasing. So where is a local maximum? -1. And if they want the value, then you got to give them the actual y value. Where are you, where do you have a local minimum? 1. All right, B. B says, find the interval which f is concave up or concave down, and find all inflection points. Okay, B says, find concave up, concave down, and are there inflection points? Whenever they say concave up, concave down, or inflection points, it just means second derivative. So we are going to find second derivative, and we're going to make it equal to 0 or undefined, and then do another sign chart. So it's kind of the same thing. So go ahead and do that. Here are my potential inflection points. What makes second derivative 0? 0. Okay, and then how does the sign go on the sign chart?
Negative and then positive.
Negative and then positive. On the sign chart for second derivative, you shouldn't draw down and up like that, because we're not talking about increasing, decreasing. We're talking about concavity. So you should draw down and up like that. Concave down, concave up. Okay, so the question is, where are you concaving? So let's say concave down. Where is it concave down? To 0, and then we don't include 0, okay? So be careful on that. And then concave up. 0 to infinity. Is there an inflection point?
Yes.
Yes. How do you know there's an inflection point? The sign change on what? On second derivative. Yeah. Okay, so they will always ask you to justify. Okay, how did you know that this is an inflection point? It is because the sign changed on second derivative. Okay, inflection point is x equals to 0 because second derivative changed signs. At 0, yeah. It changed from negative to positive at 0. For second derivative. The last part is the hardest part, I think. It's basically use all you have in A and B, and you have to sketch the graph of the original graph. Okay, C. All right, so what you're going to do is kind of draw in all the interesting points. That's your critical points, and then your inflection point. Okay, this is the part I don't like. Okay, so I'm going to draw a sign chart that has all 3 points. And then hopefully I can figure out how this looks like. Okay, so my graph goes up, down, and there is a big concavity down, and then concave up. Okay, so from the left of -1, my graph is gonna go up. And then once it reaches -1, it's gonna go down. Huh? And then at 0, it's gonna increase. Okay.
The fx, it says x plus 1 squared.
Oh, I'm sorry. I think I drew this wrong.
-1 is a 0.
-1 is a 0. Yeah, sorry.
It's a
Ooh.
bounce thing.
Okay, so up and then, sorry, up and then, oh, I'm sorry. Did this wrong. Up and then down and up, like that. Okay, so at 0, there's a concavity change, but I'm still gonna go down. And then at 1, it's a minimum, and then I'm going to go up. So this should be my original graph. Can you guys see that?
For the -1,
Yeah.
just reach to the 0 and then go back to minus.
We don't know where it's going to go. We just know it's a maximum. We don't know the actual value unless you plug into the original graph. Yeah. So if we are only given these two sign charts, this is kind of how the shape of the graph will look like. If you want to know exactly how it's going to look like, you have to plug in values. Yes? No? Any questions on sketching this graph? We're going to sketch a lot of graphs for the next few days. Yes, no? Okay. All right, let's stop here for now.